Hello students, let us solve some more problems from the exercise 1.1, that is question number 8, 9 and 10. So first of all, let us solve the question number 8. It says that so that the relation R on the set A containing 1, 2, 3, 4, 5 given by R is equal to AB order pair such that mod of A minus B is even is an equivalence relation. This relation which is defined on the set A is an equivalence relation. Again, we have to show that the elements of the set 1, 3, 5 are related to each other, as well as the elements of the set 2, 4 are also related to one another. But no element of the set 1, 3, 5 is related to any element of the set 2, 4. Okay, let us solve it. So, you see that the relation R which has been defined on the set A is like this: modulus of A minus B is even. Means if you take the difference between two elements, then you will get the difference as even. Okay? So, let us write the relation first. Here R is equal to 1 1, then 1 3, 1 5, 1 1, 1 3, 1 5, 2 2, 2 4, 3 1, 3 3, 3 5, then 4 2, 4 4, 5 1, 5 3 and 5 5. This is the required relation. Okay, we have to check that this is an equivalence relation. You know that a relation is said to be equivalence if it is simultaneously reflexive, symmetric and transitive. That means we have to show this relation R is reflexive, symmetric and transitive. So let us check for reflexivity. Reflexivity. Let X belongs to the set A. X is any arbitrary element of the set A. That means here X may be 1, it may be 2, it may be 3, it may be 4 or it may be 5. Then we know that X minus X is equal to 0. The difference between the element X with itself is equal to 0, and if we take its modulus, then modulus is also 0, which is even. Here you know that 0 is even. Therefore we can say that X is related to X, that is XX order pair belongs to R, and this relation holds good for any element of the set A, that is for all X belongs to the set A. This pair stands for 1 1 if X is equal to 1, 2 2 if X is equal to 2, then 3 3, 4 4, 5 5, this much only. Therefore this relation R, therefore we can write that R is reflexive. R is reflexive. Then come to symmetric. For symmetric, we have to take two arbitrary elements of the set A. Let X, Y belongs to the set A. X and Y are any arbitrary element of the set A. But you cannot take, suppose X is equal to, if you take X is equal to 1, you cannot take Y as a 2 or 4, because in that case the difference is not even. So we have to take x and y, two elements from the set A, in such a manner that xy order pair such that xy order pair belongs to R. Means if you take x is equal to 1, then y may be 1, okay, or y may be 5 like that, or y may be 3. Okay. So if x and y belongs to A such that xy order pair belongs to R. This implies what is the relation between x and y? Suppose here you see AB order pair belongs to R. Then what is the relation between A and B? That the modulus of A minus B is even. Here the order pair xy belongs to R. It means that the modulus of the difference of x and y must be even. That means we can write mod of x minus y is even. This rule, this one. Then if we take common minus here, then x minus y would be y minus x. So mod of y minus x minus of y minus x is even. This one is same as this one. That implies modulus of suppose you know that mod of x is equal to mod of minus x. Similar is the case here. That means we can write mod of y minus x is even. That implies yx order pair belongs to R. Why? Because you see here mod of A minus B is even. So it means that the order pair A and B is an element of the set R. Similar is the case here. Mod of y minus x is even. Therefore, if you take the order pair yx, y as first component, x as second component, then it must be an element of the set R. Therefore, yx order pair belongs to R. We have started here that xy order pair belongs to R, but ultimately we get here that yx order pair belongs to R. This is the definition of symmetricity. Therefore, we can say that R is symmetric. Okay. Then go to transitive. For transitive, we have to take any arbitrary 3 elements from the set A. So let x, y, z belongs to the set A such that xy order pair belongs to R and yz order pair belongs to R. That implies xy order pair belongs to R. What does it mean? It means modulus of x minus y must be even. So x minus y's modulus is even. And for this, since yz belongs to R, we can say that the modulus of difference of y and z is also even. That is y minus z, mod of y minus z is even. So that implies we can write modulus of x minus y is even. Means we can write x minus y is equal to plus minus 2m, and for this we can write y minus z is equal to plus minus 2n, where m comma n belongs to the set of a natural number, where m and n are some natural numbers. Okay. Then add these two relations. This one and this one. So that implies x minus y, this one, plus y minus z. Let us take the sum of these two expressions. Now our right hand side would be equal to plus minus 2m, again plus minus 2n. For this one, its value is plus minus 2m and its value is plus minus 2n. ठीक है. Look at the left hand side. Here we have minus y and plus y. So they can be cancelled out. And the remaining terms are x minus z. It is equal to, in the right hand side, plus minus 2 is the common. So take plus minus 2 common. So inside the bracket we can write m plus n. That means we can write modulus of x minus z is even. Modulus of x minus z is even, because here 2 is there. Any number which is divisible by 2 is even. So mod of x minus z is even. That means we can write, what is the relation between x and z? That the modulus of x minus z is even, means the xz order pair must be an element of the relation R. So we can write that xz order pair belongs to R. We had started that xy order pair belongs to R and yz order pair belongs to R, and ultimately we got xz order pair belongs to R, and this is the condition for transitiveness. Therefore we can say that R is transitive. Therefore R is transitive. Okay. Again, since R is reflexive, symmetric and transitive, therefore R is an equivalence relation. ठीक है. Then come to the next part. It says that the elements of the set 1, 3, 5 are related to each other. How? Write down. We know that the difference between any two odd integers is always even, and also the difference between any two even integers is even. Therefore all the elements of 1, 3, 5 are related to each other, and all the elements of the set 2, 4 are related to each other. ठीक है. But the difference between an odd integer and an even integer is always odd. therefore no element of the set 1 3 5, the set containing odd integer, is related to any element of the set 2 4. ठीक है, no element of the set 1 3 5 is related to any element of the set 2 4. You take for example 1. If with 1 we take 2, then what is the difference? 1 minus 2, modulus of 1 minus 2, it is equal to 1. 1 is odd. If you take 4 with 1, that is 1 minus 4, modulus of 1 minus 4 is equal to 3, which is also odd. So if you take any element of this set and any element of this set, you make a pair, then and take the difference between them and also their modulus, then you will get an odd integer, not even. But here the pair should be is that the difference between the two elements is even. But the difference between any element of this set and this set is not even. Therefore no element of this set is related to this set. ठीक है, then go to next question. So that each of the relation R in the set A is equal to x belongs to z such that 0 less than equal to x less than equal to 12, given by R is equal to AB order pair such that modulus of A minus B is a multiple of 4. This is the first question. And the second one is AB order pair such that A is equal to B. We have to show that these two relations are equivalence relations defined on the set A containing the integer starting from 0 to 12. ठीक है, again in each case we have to find the set of elements related to the element 1. In each relation we have to find the set of elements which are related to 1, that is the equivalence class of 1. We have to find in the last, we have to find the equivalent class of 1 for each question. ठीक है, अच्छा, let us solve the first one. I. Here we are given that A is equal to 0 1 2 dot 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 12. These are the elements, these are the integers which are the elements of the set A. And in this set A we are given a relation R like this, that AB order pair such that modulus of A minus B is a multiple of 4. Multiple of 4. You see, if we write the set R in the roster form, then how many elements would be there? There would be, you see here that there are 13 elements in the set A. 13 elements. If you take 0 0, 0 minus 0 is 0, 0 is a multiple of 4. If you take 1, then we will get 1 1, 1 minus 1 is 0, 0 is a multiple of 4. So 0 0 pair, 1 1 2 2 up to 12 12, that is 13 pair would be there. Again, if we take 1 and 5, suppose 1 and 5, if you take 1 and 5, okay, then the difference of 1 and 5 is 4. Modulus of 1 minus 5 is 4, and 4 is a multiple of 4. If we take 1 9, it is also a multiple of 4. The difference between these two is also a multiple of 4. So in this way we will get 1 5, 1 9, then 5 1, 5 1, 9 1. Okay, then 9 5, 5 9. So these are 6 elements. So altogether we will get 13 plus 9, that is 13 plus 6, sorry, sub 6 element, that is 19 element. If we write this set in roster form, then we have to enlist 19 element for this relation. But we don't need to write R in the roster form. We need only to show that this is an equivalence relation. That means we have to show that this is reflexive, symmetric and transitive. Okay, so let us check for reflexivity. Reflexivity. For reflexivity, we have to show that for any element belonging to the set A, that element should be related to itself 0, 0, 1, 1, 2, 2 up to 12, 12. Okay. For that, we have to take any arbitrary element x from the set A. So write down, let x belongs to the set A. Then x minus x, modulus of x minus x, which is equal to 0, and this 0 is a multiple of, which is a multiple of 4. Okay, this here you see that x is an element of the set A, means the value of x may be 0, may be 1, may be 2 or may be 12. That means here we can write 0, 0 or 1, 1, 2, 2, 3, 3 up to 12, 12. So that implies we can write xx order pair. Since mod of x minus x is equal to 0, which is a multiple of 4, we can write that xx order pair belongs to R, and this stands for all x. So we can write for all x belongs to the set A. Okay, we have written only one pair here, but this one pair represents 13 pair, 0, 0, 1, 1, 2, 2 up to 12, 12. Therefore, we can write that R is reflexive. R is reflexive. Okay, then come to symmetric. Symmetric. For symmetric, we have to choose any arbitrary two arbitrary elements of the set A. So write down, let x comma y belongs to the set A such that xy order pair belongs to R. Xy order pair belongs to R. It means that modulus of x minus y is a multiple of 4. That implies x minus y is equal to plus minus 4m, where we can write that m belongs to z. M is an integer, so x minus y is equal to plus minus 4m. So that implies y minus x is equal to minus plus 4m. Y minus x is equal to minus plus 4m. That implies modulus of y minus x. We can take modulus of y minus x is a multiple of 4. That implies yx order pair belongs to R. Okay, therefore R is symmetric. This is very simple. Okay, so symmetric is complete. Then come to transitive. For transitiveness, we have to choose any 3 arbitrary element from the set A. So write down, let x, y, z belongs to A such that xy order pair belongs to R and yz order pair belongs to R. It means that mod of x minus y is a multiple of 4 and y minus z is a modulus of y minus z is a multiple of 4. That implies x minus y is equal to plus minus 4m and y minus z is equal to plus minus 4n, where m comma n belongs to z. m and n are any two integers. ठीक है, let us add these two relations. That implies x minus y plus y minus z is equal to plus minus 4m, again plus minus 4m. In the left hand side we see that minus y and plus y, they are cancelling each other and the remaining terms are x minus z. In the right hand side plus minus 4 is common, so take plus minus 4 common. Inside the bracket write down m plus n. You see here x minus z is a multiple of 4, means modulus of x minus z must be a multiple of 4. It is divided by 4. Therefore we can write the mode of x minus z is a multiple of 4. That means if we take the xz order pair, then it is an element of the relation R. Therefore R is transitive. R is transitive. ठीक है? Okay. So since R is reflexive, we can write since R is reflexive, symmetric and transitive, therefore it is an equivalence relation. ठीक है? Then come to the second part of this question, that we have to calculate the set of all elements which are related to the element 1. Then here equivalence class of 1, the set of all the elements related to this 1. Now think, if I take 1 with 1, then 1 1 order pair must belongs to R. Why? Because 1 minus 1 is equal to 0. So mod of 1 minus 1 is 0, which is a multiple of 4. If I take suppose 1 5, then what is the difference between 1 and 5? 1 minus 5, which is equal to 4. So minus 4, which is equal to plus 4, modulus is positive. So 4 is a multiple of 4. If I take 9, then 1 minus 9, 1 minus 9, minus 8, and minus 8 is divisible by 4. So minus 8, modulus of minus 8 is plus 8, which is divisible by 4. So 1 9 pair must be there. So we can write that the equivalence class of 1 is the set containing 1, 5 and 9. Okay, if you take any element of this set with 1, then that pair must belong to the relation R. You take 1 1, 1 5, 1 9, 5 1, 5 5, 9 9, 9 5, 5 9 and so on. The difference between those two elements must be a multiple of 4. Therefore we can say that the set the equivalence class of 1 contains these 3 elements. So this is the required answer. Okay, then come to the second question. R is equal to AB order pair such that A is equal to B, and this relation is very very simple. You can solve this question by yourself. So try yourself. This is very similar to that one. It is very very easy. You can easily solve. Okay, thank you. So next, going to go to the next question, that is 10. Question number 10. It says that you have to give some examples. That give an example of a relation which is symmetric but neither reflexive nor transitive. Second question, transitive but neither reflexive nor symmetric. Third question, reflexive and symmetric but not transitive. Fourth one is reflexive and transitive but not symmetric. And the last one is symmetric and transitive but not reflexive. We have to give example of such type of relations. For that we have to take the help of any particular set. For example, take the set A. Let the set A contains 1, 2, 3, only 3 elements, 1, 2, 3. Let A is equal to 1, 2, 3. Then define a relation R. First, R is equal to, we have to write down a relation which is defined on this set A, that which is symmetric but not reflexive, neither reflexive nor transitive. The relation would be symmetric. Okay, it would be symmetric but neither reflexive nor transitive. So for example, let us take 1, 2, 1, 2, then take the second pair 2, 1. Okay, this much only. You see here the order pair 1, 2 is there. Its reverse is 2, 1 and 2, 1 is here. Sorry, 1, 2 का reverse 2, 1, 2, 1 is present. 2, 1 का reverse क्या है? 1, 2. 1, 2 is also here. So this relation definitely we can say that this is a symmetric relation. But this is not reflexive. Why? Because 1 belongs to the set A, but 1, 1 pair is not here. 1, 1 is absent, and that is sufficient for reflexivity. Okay, this is not reflexive. For reflexivity, for reflexive relation, the relation R should contain 1, 1 pair, 2, 2 pair, 3, 3 pair, this much. Okay, but 1, 1, 2, 2, 3, 3 pair are not there. Therefore we can say that this relation is only symmetric, but this is not reflexive or transitive. For transitive, for example, here you see that 1 is related to 2 and 2 is related to 1. So the third pair must be 1, 1, but 1, 1 is absent here. So it is not transitive. It is only simply symmetric. Okay? Then go to second example. Second, we have to give the example of a relation which is transitive but neither reflexive nor symmetric. Transitive. Transitive but neither reflexive nor symmetric. Okay, so let us take the element 1, 2, 2, 3 and 1, 3. This much only. You see here, this is not reflexive. Why? Because 1 is there in the set A, 1 is in 1, 1 order pair is not here, so it is not reflexive. Again, you see 1, 2 pair is there, but 2, 1 pair is absent here, so it is not symmetric. But it is transitive. Why? Because you see here 1 is related to 2 and 2 is related to 3. You cancel these 2. The third pair should be 1, 3 and 1, 3 is present here. So we can say that this relation is transitive. It is neither reflexive nor symmetric. Only transitive. Then come to third example. It says that we have to give the example of a relation which is both reflexive and symmetric but not transitive. It is reflexive and symmetric but not transitive. This is very, very important. Okay, this one out of these all questions, this one is very important. Since we have to give a relation which is reflexive on this set, so first of all we have to take 1, 1, 2, 2 and 3, 3. These 3 elements must be taken, otherwise it would not be reflexive. For reflexive, we must have to take all these 3 elements. Then it says that the relation should be symmetric. So suppose let us take 1, 2. If we take 1, 2, then we must take its reverse, that is 2, 1. Okay, but you see here 1 is related to 2 and 2 is related to 1. So if 2, 2 cancel, then 1, 1 pair is here, then it is transitive. Okay, but we have to give such an example of a relation which is not transitive. Now in this case it is transitive. So again we have to take some other elements. Suppose take 2, 3. 2, 3. For symmetric we have to take its reverse, that is 3, 2. Now this relation, you can say this relation definitely reflexive, symmetric but not transitive. Why? Because for transitive you see that here you see that 3, 2 pair, 3, 2 pair take this element and this element. 3 is related to 2. I am writing here 3 2 and 2 1, these two elements. Here 2 2 common. Okay, so the third pair should be 3 1. 3 1 should be there, but you see here there is no 3 1. So definitely this relation is not transitive, because the rule of transitiveness is violated here. Okay, 3 2 pair is there, 2 1 pair is there, but 3 1 pair is absent. Therefore this relation is not transitive one. But since it contains 1 1 2 2 3 3, therefore it is reflexive. Okay, all the elements of the set A are related to each other. And if you reverse any element, if you reverse 1 1, it is 1 1. But in the set theory, repetition is not allowed, so we don't need to write 1 1 twice. Similar is the case here and here. For this one, if you reverse this one, then you will get this one. If you reverse this one, then you will get this one. For these two elements, 2 3, its reverse is 3 2, and 3 2, its reverse is 2 3. So we can say that this relation is symmetric, reflexive, symmetric, but not transitive. Then come to the fourth one. The relation fourth one should be reflexive and transitive, but not symmetric. Reflexive and transitive, but not symmetric. IV. Let R is equal to 1 1. For reflexive, I have already told you, you have to take minimum 3 elements, 1 1, 2 2, and 3 3. Otherwise, it will not be reflexive. So for reflexivity, we must have to take these 3 elements. Then come to transitive. Okay, it should be transitive, but not symmetric. For transitive, for example, let us take 1 2, then 2 3, 1 2 2 3, and then take 1 3. Okay, this much only. You see here carefully that 1 1 2 2 3 3 pairs are there. Therefore, it is reflexive. 1 is related to 2 and 2 is related to 3. These 2, if you cancel these 2, then the third pair should be 1 3. I have taken here 1 3. So it is transitive. But it is not symmetric. Why? Because 1 2 is there. Its reverse is 2 1. 2 is not here. 2 1 order pair is absent here. Therefore, this relation is reflexive and transitive, but not symmetric. Then come to the last question, that is V. We have to give an example of a relation which is symmetric and transitive, but not reflexive. This relation is very, very simple. A relation which is symmetric and transitive, but not reflexive. It is very, very simple. How? You see, for symmetric, suppose we have to take 1 2 and 2 1. 1 2 pair, its reverse is 2 1. 2 1, its reverse is 1 2. So if we write these two elements, if we take these two elements, then it would be symmetric. For transitive, you see here 1 is related to 2 and 2 is related to 1. So 2 2 must, if you cancel 2 2, then our third pair should be 1 1 for transitiveness. So let us take the element 1 1. Okay? Then take this much only. Okay? Here this relation, if this relation has 3 elements, 1 2 2 1 and 1 1. I am saying that this relation is symmetric. How? If you reverse any element, the answer would be present there. 1 2, its reverse is 2 1. 2 1 is here. 2 1, its reverse is 1 2. 1 2 is here. Third element is 1 1. If you reverse 1 1, then you will also get 1 1. So if the reverse of any element, the reverse of all these 3 elements are present here, therefore it is symmetric. And it is transitive because 1 is related to 2 and 2 is related to 1. So 1 1 present is pair is here, therefore it is transitive, but it is not reflexive. Why? Because for reflexivity we should have 1 1. You can say that 1 1 is here, but 1 1 is not sufficient. For reflexivity, we should have 1 1 pair, 2 2 pair, 3 3 pair. All these 3 pair must be there. 1 pair, 2 pair and 3 pair. All these 3 elements must be there in the relation R for reflexivity. Okay, if at least one of them is absent in the relation, then definitely you can say that that relation is never reflexive. Okay, so these are the examples of the relations which we are asked to find out. So students, this much for today. In the next class we will solve some important problems from the previous year's board questions. So if you like this video, so please share this with your friends. Please subscribe this channel if you haven't subscribed yet, and also like it.